Now that we've talked about arcs of circles, we've talked about angles of circles, finally we have to talk about segments that can exist in circles. So we have a few definitions and then 3 different relationships that we're going to look at. Before we can talk about those relationships, though, we need some definitions to be able to talk about the segments with. So here are the 3 of them. We have segments of a chord, we have secant segments, and we have external segments. So all these are going to make sense more in context. So if I have a circle, segments of a chord are these. So if I have 2 segments that intersect each other, these are both chords, and what I have then are 4 segments of chords. So these are the segments created when 2 chords intersect in the interior of a segment. So I have 1, 2, 3, 4, A, B, C, and D, 4 segments of chords here. The next 2 kind of go together. So if I have another circle, here, secant segments are segments that contain the chord, contains the chord of a circle and has exactly 1 endpoint outside the circle. So again, this is kind of tough to conceptualize here without seeing it. And so I'll actually draw 2 of them here. So this is one, and this is another. So secant segments are, like we just said, the segments that contain a chord. So here's one chord, here's another chord. Contain the chords of a circle and has exactly 1 endpoint outside the circle. So here we go. There's my endpoint outside the circle. So this entire thing from here to here, this is all a secant segment. That's what it is. And then the external segment is just a part of the secant segment that is outside of the circle. So the external segment is just this portion right here. So just the portion that's outside the circle. And so really, I've got 2 different kind of segments going on. Actually, well, 3. The entire thing is the secant segment. The inner part is the chord. And then the outer part is called the external segment. So these are the 3 different segments that we're going to be talking about as we move forward. And so just naming them, of course, isn't that interesting. But actually now we have to justify something with them. So here's what that is going to look like. So I'm going to talk about my segments of chords to begin with. And I really need to nail this circle here. So let's go for this. Well, you know what? Why not? Let's go crazy. On the spot, let's find, I have a circle tool here someplace. Here's a circle. Okay, how do I do this? Oh, okay, that's, I'll take it. All right, so here's my circle. Here's my circle, and I'm going to draw, and man, this is life-changing. I'm going to draw a chord within it. Here it is. There we go. And here is another one. So these are my 2 chords. So here's what's going on here. I have created a circle with these 2 chords and 4, of course, segments of chords. What is the relationship that exists between them? And it's not obvious. It's not obvious at all that this is going to exist. It's going to sound, if I were to just tell you what it is, it's going to sound like it's just kind of made up. But so let's add actually something else in that might help us. And that would be our, long ago friend, the similar triangle. So what I've got here are 2 similar triangles. Let me justify why. So if I connect these 2 segments, I create these triangles here, of which this angle right in here, now how do I, all right, let's go back, stop it. This angle right in here and this angle right in here both create the same arc, which will make them congruent to each other. This angle in here and this angle in here will make this arc right here, so they will be congruent to each other. And then that's all we really need, but let's just go ahead and finish this off. These 2 angles in here are, of course, vertical angles, and so they will be congruent to each other as well. And so what we've got here are 2 triangles that are similar to each other by angle. And so what does that mean for us? What interesting things does that mean for us? Well, let me label these again. So A, B, and C, and D. So A and C make up one of my chords, and B and D make up the other. But I can write a statement of proportionality here because of my similar triangles. What it'll say is that A over C. So actually, that's a lie. That's not what I want. That's a lie. Go back. A over its corresponding part, B, that's better, is going to be equal to and then so let's see, A over B is going to be equal to D over C. So this is just my similarity, or sorry, my statement of proportionality of these two similar triangles for the things that I have marked. And so if I rearrange this slightly, if I cross multiply, what I'll get is that A times C is going to be equal to B times D. And what that means is that the two parts of one chord, if I multiply them together, will be equal to the two parts of the other chord. A times C, two segments of a chord, and B times D, two segments of a chord. Their products will always be the same. And it's all just because of these similar triangles I have set up. Okay, so that's situation number one of my segments here. Here's situation number two. So situation number two is, all right, let's see if I can nail this again. Let's make another circle. And, okay, so situation number two, oh, that's not exactly where I wanted it, but we'll take it. So if I have another circle here, and I've got, so we're going to go with 2. Am I off? How much am I off by? Let's find out. If I have 2, dang. If I have 2 secant segments, so let me do this, fine, it's fine. It's a learning process. Draw my circle again. I have 2 secant segments. Here's one, and here's the other. Perfect. Okay, let's talk about the relationship that exists here. So, just like before, if I just gave you what it was, it would be totally non-intuitive. But again, we're going to make some similar triangles. So I'm going to connect this point to this point and this one to this one. Okay. So this is going to be kind of tough and a little bit tricky to see. But just if we follow along here, let's find some angles that are congruent to each other. Well, so it's not obvious because I'm not going to be able to link two angles that are congruent right away. But we should be able to see our two triangles. I've got and I'll just highlight these really quick. No, I won't. Undo that. Go away. Go away, please. If I highlight these two triangles. So I'm talking about this triangle, the small triangle, and then the big triangle here. These are two triangles I'm going to try to justify being similar again. So obviously they share this angle. That's no big deal. It's going to be congruent to itself. So what's another one that I can find? Well, we have to go back and think about what we know about inscribed quadrilaterals within circles. And that is the fact that their opposite angles will be supplementary to each other. So this angle right here will be supplementary to this angle right here. And so the question is, can I find another angle that's supplementary to this one right here? And I can. It's on the other side of this line. So here we go. This is a connection I can make, and this is totally not obvious. It's a little bit tricky. But these two angles, all right, so this angle right here, this inscribed angle, and then this, I don't know what to call this, non-inscribed angle over here are going to be congruent to each other. And so the same thing will be true. I could use the same exact logic to talk about this angle and this angle. And then as we already said, this one will be congruent to itself. Oh, that didn't show up very well. So what I've got then again are two similar triangles. And now I just have to be really careful about how I label these and figure out what my similarity is. So A and B and C and D. Okay. So let's find the corresponding parts this time. So A, so just this portion of my triangle. A, the corresponding part in the other triangle is this entire side. So C plus D. And that'll be equal to, all right, so let me use a different color. This outer portion, C, over, and this entire thing, A plus B. And so if I cross multiply again, what I will find is that A times A plus B. All right, so the external part of my secant segment times the entire thing will be equivalent to, and then C, my external segment, times, and then once again the entire thing, which is C plus D. All right, so this is my second, so this is 1, this was 2 of my theorems here about the parts of the segments within circles. I have one more that I have to knock out here. So let's just do one more. And this one will be kind of straight follows from the previous. But let me go ahead and make it. See, I feel like I've lost some time making circles, but what I've learned can only speed me up in the future, which is great. So here's my last situation. It is this. What if I have a secant segment and a tangent segment that I'm going to talk about? So just like before, I'm going to find my similar triangles. So I'm going to draw in these parts. And what I'm going to get again are similar triangles, and let's just justify why. So obviously this thing will be congruent to itself. Okay, so this one's a little bit tougher to see. What do I have here? Well, this angle right here. Oh, see, now I'm doing it again. I'll get better, I promise. This angle right here, and then this is congruent to itself, and this angle right here. Okay, its intercepted arc is this portion. This portion right here is the intercepted arc. You know who else's intercepted arc that is? The tangent and the chord. That'll make these two angles congruent to each other again. So once again, I have similar triangles. The other way of thinking about this is that this is the same thing as my two secant segments. It's just that my chord, my internal part this time, is 0. I only have the external portion, which we'll see I think will be slightly obvious when I go and actually label these. So A and B and C. All right, so A is to C in the same way that C is to A plus B. So I'm going to write this as, so A times A plus B. So the external part times the entire secant segment is going to be equal to, and then C times C. And I can think about it the exact same way. The external part, C, times the entire thing, C. There's no internal part this time. So I would make the argument that these two things are exactly the same, but just one doesn't have this other inner part to go along with it. So these are my 3 theorems that have to do with chords and secant segments within circles. Now it's just a question of how can we apply these and what problems can we solve with them.